We have learned that a linear equation in two variables represents a straight line. For a pair of linear equations in two variables, there can be one of the three possibilities. The lines representing them may intersect or overlap or may be parallel. Intersecting lines represents a case of unique solution. Coincident lines represent infinite solution and the parallel lines represent the case of no solution. As in case of equations with two variables, solution of equations with three variables too can be categorized in one of the three categories, namely unique solution, infinite solution, no solution. We can visualize the solution types of equations of three variables by representing the system of equations graphically. A linear equation in three variables represents a plane in 3D space. Now, the graphs of the three equations in the system of equations will represent three planes. In most cases, these planes intersect at a single point in coordinate space as shown here. They may intersect in a line, or all of them may coincide as shown. And lastly, the three planes may not intersect at a common point. Here, the first condition represents a unique solution. The second condition represents the case of infinite solutions. And third case represents a no solution case. A system of equations is called consistent if it has unique or infinite solutions, and it is called inconsistent if it does not have a solution set. So far, we have learned how to solve a system of equations in two variables, both graphically and algebraically. Equations in 2 and 3 variables can be solved by using matrices and determinants as well. Let's use the matrices and determinants to solve the system of equations. Although we study matrices before determinants, historically, determinants are earlier than matrices. Determinants were first used in the 3rd century BC in Chinese math textbook, the 9 chapters on the mathematical art. A determinant was defined as the property of a linear equation, and it determines whether the system of equations has a unique solution. Let's consider the system of linear equations in 3 variables and see how to solve those by using matrices and determinants. If we take the coefficient matrix as capital A, variable matrix as capital X, and the constants as matrix capital B, given system of equations can be represented in matrix form as shown here. Let's call it equation 1. Now, there are two possible cases for a square matrix A, which is it may be singular or may not be singular. Recall a matrix is singular if the associated determinant is 0. First, let's take the case when A is non-singular. Matrix A being non-singular implies that inverse of matrix A exists. Pre-multiplying both the sides of the equation 1 by A inverse, we get the equation as shown. Further, using associative property of matrix multiplication, we have coefficient matrix X equal to A inverse multiplied by matrix B. Since the inverse of the matrix A is unique, equation x equals A inverse multiplied by B gives the unique solution to the system of equations. In other words, the system of equations is consistent. Next, let's consider the second case when matrix A is singular. When A is singular, A inverse does not exist. So, in this case, we compute adjoint of matrix A and multiply the same with matrix B. If the adjoint of matrix A multiplied by matrix B gives a non-zero matrix, then the system of equations does not have the solution, or, in other words, system is inconsistent. Next, if the adjoint of matrix A multiplied by matrix B gives a null matrix, then the system of equations have infinitely many solutions. In this case too, the system of equations will be consistent. So, depending upon the value of determinant associated with square matrix A, the system of equations is consistent or inconsistent. We can apply this learning to solve any system of linear equations graphically. The first step will be to write the system of equations in the form of matrix equations Ax equals B. Next, find the value of determinant associated with matrix A and check if its value could be 0 or non-zero. If the value of determinant of A is non-zero, then the system has a unique solution given by solving the equation x equals A inverse multiplied by B. And if the value of determinant of A is 0, then there could be two possible cases giving no solution or infinitely many solutions. Let's solve some problems.